Linear programming is a valuable tool for decision making. We often use it to optimize a process. For example, we may want to maximize profit, minimize cost, minimize downtime, things like that. The objective function is whatever we are trying to maximize or minimize. The constraints are other limitations. Often these are inequalities. For example, if we have a factory and we're trying to maximize the profit that we make from our widgets, surely our factory cannot make an infinite number of widgets. We will have limitations based on space, the amount of people we have hired, the capacity of our machines, things like that. Those are constraints. When we put the constraints together with the objective function, we have a mathematical model. There are many methods of solving mathematical models and linear programming problems. For simple models that only have two variables, we can use a graphical method in which we graph lines and inequalities, and we use those to determine where our optimum occurs. We'll be using what we call the corner point theorem. We will graph a feasible region, just like you've done before when you've graphed the solution region for systems of inequalities. We know that we call it a bounded region if it can be enclosed in a circle. Turns out, if it can be enclosed in a circle, then the objective function has a maximum and a minimum, and those occur at one or more corner points. If it's unbounded, it may not have a maximum or a minimum. Usually it will have one and not the other. But if it does, it will occur at one or more corner points. It will not occur in the middle of the region. That's the idea. Let's draw a little picture to try to illustrate this. First of all, let me show you. Let's do an example first, then we'll come back and we'll go back to the corner point theorem. Okay, general process. What we're going to do is, if we're creating our own model, it may be helpful to summarize the data in a table. This step is optional. Then we're going to create the mathematical model, and we're going to write down the decision variables, the objective function, the constraints, and any non-negative constraints. Then we're going to graph the feasible region and find the corner points like we've done before. Then we're going to determine the objective function at each corner point, and then we're going to determine the optimal solution, if it exists, and then we're going to interpret that in terms of the original problem. Let's look at this mathematical model. Okay, minimize c equals 100x1 plus 300x2. We call this the objective function. And we call these the constraints. Okay, the first thing that we need to do is to graph the feasible region dictated by our constraints. So if we start with this first one, so 2x1 plus x2 equals 6, we start by setting our x1 equal to 0. So then what's our y, or our x2? 6. Then we're going to set our x2 equal to 0. So what's our x1? We have 2x equals 6, and so x1 is equal to 3. Then we move to the next one. If we set our first variable equal to 0, then our x2 is 3. If we set that x2 equal to 0, our x1 is 6. If we set our first x1 equal to 0, then x2 is 2. And then if we set our x2 equal to 0, then our x1 is going to be 8. These are what we call our non-negative constraints, and these are going to put us into quadrant 1. Okay, so I put my scale on my graph. So I know that my Looks like my y's, I need to go up to 6. So 1, 2, 3, 4, 5, 6. You'll find your life easier if you spread yourself out a little bit. And my x's need to go out to 8. So 1, 2, 3, 4, 5, 6, 7, 8. So we graph the first one that goes through 0, 6 and 3, 0. We don't have any dashed lines here. So here's our first constraint, and I'm going to label it 2x1 plus x2 equals 6. Remember, we're just thinking of x1 and x2 as being x and y. And then we're going to do 0, 3, 6, 0. So this gives me my 2x1 plus 4x2 equals 12. And then last we have 0, 2, and 8, 0. So here I have x1 plus 4x2 equals 8. Now I need to figure out my shading. Once again, I will use the test point of 0, 0 for all of these because the origin's not on any of the lines. And so if I look at the first one, if I put that in, I get 0 greater than or equal to 6, which is false. And that means that I'm going to shade away from the origin. So that's this one. And I move to the second one. When I put in my 0, 0, I get 0 greater than or equal to 12, which is also false. So once again, I'm going to shade away from the origin. Okay, and I'm looking to see which one it is because I've labeled my lines. So this one gets shaded away from the origin. And now we look at the third one. We put in 0, 0, I get 0 greater than or equal to 8, which is also false. So once again, we shade away from the origin. So all of these are getting shaded away from the origin. So what area fits all of them? Don't forget your non-negative constraints, which are placing us into quadrant 1. The area that fits all of them will be this area way out here. So I'm going to make sure my shading is real clear and that we can see the boundaries. Make sure you shade all the way over to those axes so that the reader can see that it doesn't continue beyond the first quadrant. And so then everything out here will be shaded. Let's do red. Okay, so all of this out here will be shaded. Okay, so that's my feasible regions, everything out here. This is an unbounded region, right? Because I cannot enclose it in a circle. Okay, so now what I need to do is I need to find all my corner points. So first I'm going to just mark them on here so I know what they are. There's probably going to be some, very likely, that you can just pull off the graph easily. Okay, we can pull off. This one's easy, that's 8, 0. This one's easy, that's 0, 6, but we need to find this one, and we need to find this one. So we need to intersect those two lines and use substitution and elimination to find where they intersect. So if we start with this one, I'll label A. We have 2x1 plus 4x2 equals 12. That's one of the lines that goes through A. What else goes through lines? Through point A. This one. 2x1 plus x2 equals 6. So you can do substitution elimination on these. I'm actually going to notice that my coefficient for x1 is in the same for both of them, so I'm going to go ahead and subtract these two equations. So that means 2x1 minus 2x1 is 0. 4x2 minus x2 is 3x2. 12 minus 6 is 6. So x2 then is 2. Put that into one of them. And so here we've got 2x1 plus 2 equals 6. Putting into the second of those two. 2x1 equals 4, and so then x1 is 2. So this gives me the point 2, 2. Let's look at corner point B. Let me label it. Here's corner point B, the second of those two. So what lines is this on? This is on x1 plus 4x2 equals 8. And it is also on 2x1 plus 4x2 equals 12. This is why it's very important to label your lines. Once again, it looks like if I subtract the equations, I can get one of the variables to go away, this time x2. And so x1 minus 2x2, this gives me negative 1x1. 8 minus 12 gives me negative 4, so x1 then is positive 4. Put that into one of your equations. So 4 plus 4 x1 is equal to 8. Subtract 4 from both sides. And so then x1 is 1. And so that gives me the point 1, 4. We want to look at our graph to see if that makes any sense. And it doesn't, because I got my variables mixed up. Do you see that? I put my 4 into my equation in place of the x1, but I did not write x1 where I should have, or I wrote x1 where I should have written x2. So really this should be x2 equals 1. Do you agree? So now this gives me 4, 1, which does make sense with your graph. It's very important to look to see if your corner points make sense with your graph. My 2, 2 does indeed make sense with my graph. So now what I do is I make a table of all my corner points. Okay, so let's make a table here, and let's put our objective function in the second column of our table. Okay, what was my objective function? Let's go back up. It's whatever we're trying to minimize or maximize. So 100x1 plus 300x2. 100x1 plus 300x2. And we list our corner points. So we already found 2, 2. And we already found 4, 1. There are 2 more. What are they? Here's another one. 8, 0. And here's another one, 0, 6. 8, 0, and 0, 6. Okay. What we're going to do is we are going to evaluate the objective function at each of these. So we do 100 times x1, which is 2, plus 300 times x2, which is 2. So that gives me 200 plus 600, so 800. Now I move to the next one, 100 times x1 plus 300 times x2. That gives me 700. Now 100 times 8 plus 300 times 0. So here I have 800. And then last, 100 times 0 plus 300 times 6. That gives me 1,800. Now, before we talk about a conclusion, let's go back to the corner point theorem. Here's my process. Here's my corner point theorem. We have an unbounded region right here. That means that the objective function may not have a maximum or a minimum, but if it does, it'll occur at a corner point. Okay, so here's the reason that the corner point theorem works. And let's use our objective function that we have from the example we were just working on. Here's our objective function. C equals 100 x1 plus 300 x2. Let's suppose that C is equal to 200. Okay, so now what do I have? Now I have 200 equals 100 x1 plus 300 x2. Think of this as x and x2 as y. So we can put this in our y equals mx plus b slope-intercept form. And so that gives me 300 x2 equals negative 100 x1 plus 200. Okay, if we divide everything by 300, now I have x2 equals okay, so we can think of this as x2 equals negative 1/3 x1, I'm reducing the fraction, plus 2/3, or if you like y and x better, you can think of y equals negative 1/3 x plus 2/3. Okay, so my slope is negative 1/3 and my y-intercept is 2/3. If we sketch the graph, okay, I'm going to be real rough about this and just make sure I have everything going in the right general direction. If I think of this as 2/3, let me use a straight edge. Just to make things easier to see. Okay, so let's suppose this is our 2/3. Our slope is negative, so that means we go downhill as we go from left to right. Our vertical change is 1 compared to a horizontal change of 3. So our slope's going to be more or less like this. Which we can think of a vertical change of 1, horizontal change of 3. This is when C is 200. Okay, let's suppose that C was 300. Okay, so now I have 300 equals 100 x1 plus 300 x2. If I work this out the same way I did before, if I solve for x2, Now I'm going to divide everything by 300. So this is going to give me x2. I'm still going to get a negative 1/3 x. This time I'm going to get 300 over 300, which is 1. Okay, so if I think of this as 1/3, then here's 1. Slope is still the same, so my line will be parallel. This is when C is 300. What's going to happen when C is 400? We're going to have the same slope. We're going to have a y-intercept of 4/3. So it's going to move up a little. So here we'll have C equals 400. And you can keep going. So we have basically these lines. If C happened to represent cost, these would be constant cost lines. Okay. So they're going to go out. They're all going to be parallel. So C equals 400, then this one would be C equals 500, C equals 600, equals 700, etc. Okay, now somewhere in here you have a feasible region. As I recall, whatever your feasible region is, as I recall, ours was an unbounded region that looked, and I'm not going to put it on here because I know they won't match exactly, but let's just do a what if. This is not necessarily our exact feasible region that we have, but this is the idea. Okay, if we have, first of all, let's suppose that we have a bounded feasible region somewhere. So let's just suppose this was our feasible region. Okay, this feasible region, according to the corner point theorem, since it's bounded, it's going to have both a max and a min, and those are going to occur at a corner point. Okay, well, where is the max going to occur? Right here, somewhere in between a C of 700 and 800, maybe at about C equals 750. That's going to be the max, because in between all these constant C lines that I drew, there are other constant C lines that I didn't draw. Okay, what's the minimum C in this particular region? Oh, right here, this looks like it is somewhere a little over 300, so this C is about, oh, let's say 320. That's going to be the minimum. In other words, we can think of those constant C lines marching outward, getting larger every time. They're going to keep marching out, getting larger and larger and larger. They march inward, they get smaller and smaller and smaller. And so the smallest is going to occur right at an edge. If I look somewhere in the middle of my feasible region, like maybe right about here, sorry, that's not what I meant to do. If we look somewhere in the middle of our feasible region, like right here, that is not the minimum nor the max, because it's going to be somewhere in between. We're going to have constant C lines on either side of it that are still feasible. Okay, so that's why it occurs at a corner point. Now let's suppose that we have an unbounded region. Sorry, I'm trying to erase what I have here without erasing my constant cost lines. Okay, so now let's start over and let's suppose that we have an unbounded region. And so maybe our region looks something like this. Okay, and ours that we're doing in the example we're in the middle of is similar to this. Okay, so if we do this, does this thing have a maximum? No, because this is an unbounded region. It's going to keep marching out further and further. These constant C lines, I only drew up to 800 or 900, but then they're going to keep going. We're going to have C equals 1,000,000. We're going to keep going further and further out. There is no maximum on this. But is there a minimum? Yeah, where's my minimum going to be? Looks like my minimum right here is about real close to C equal 300. That's our minimum. Now, it doesn't always occur that you will have a minimum and not a maximum, because if my constant C lines had a positive slope, they would be going a different direction, and it's possible we could end up with a maximum and not a minimum. So what you want to do is reason out what is happening to your C, or whatever your objective function is, as you go out to that unbounded direction of your feasible region. And then you can decide if you have a maximum or a minimum or both. Let's go back to our example. Here we are. So here is our area. Now, we've already drawn some constant C functions for ours, and usually you don't need to draw that many. We just did that so that you could understand how the corner point theorem works. But here, just think what's happening as we go out to this far out area of our unbounded region. x1 and x2 are getting very, very large positive numbers. As x1 and x2 become very large, what happens to the C? Well, it also becomes very large because all of our coefficients are positive. So as x1 and x2 get bigger, C is going to get bigger. That means this thing does not have a maximum. It does not have a maximum, which is nice, but of course it didn't ask us to find the maximum anyway. It asked us to find the minimum. Will it have a minimum? Yeah, because our constant C lines are going to get smaller as we get closer to the origin. And so, since it has a minimum, it will occur at one or more corner points. So we look to see which one here is the smallest. And it's this one. This is the smallest. And so that tells me that the minimum C is 700. Now what we want to do is write our answer in a clear way that includes not only the value of C, but also the x and y at which it occurs. So we say the minimum is 700 occurring when x1 is 4 and x2 is 1. That's the way that we phrase our answer. Let's do another example. Let's solve this linear programming problem. So here is what we're going to minimize. Here are our constraints. We know that x and y are greater than or equal to 0, so this is going to put me in our quadrant 1. We want to graph these lines. So if we look at 6x plus 2y equals 36, let's find our x and y intercepts. When x is 0, then y is 18. When y is 0, then x is 6. Move to the next one. 2x plus 4y equals 32. When x is 0, y is 8. When y is 0, think of covering this one up, then x is 16. Okay, and we already know that we have y equals 20 for that third constraint. That's the line associated with that inequality. And so I think I'm going to do 2 squares for 1 unit again. 2, 4, 6, 8, 10, 12, 14, 16, 2, 4, 6, 10, 12, 14, 16, and then we're going to keep going. We'll label some more as we need them. Look at the first line. We need 0, 18, So that's right here. We also need 6, 0. So here we go. Here's that line. I have 6x plus 2y equals 36. Okay, now we do the next one. So 0, 8, 16, 0. Like that. Now we need to graph y equals 20. Where is it? It's right up here. Y equals 20 will give me a horizontal line. Now we want to do the shading. For the first line, when we put in 0, 0, we're going to shade away from the origin because it will make it false. So that means we're going to shade this way. Then for the second one, we put in 0, 0 here. We're going to get 0 greater than or equal to 32, which will also make it false. So we're going to shade away from the origin. And for the third one, we don't really even need to think about a test point. We just say y has to be smaller than or equal to 20. So where will it be? Below this line. So what area will satisfy all of them? Remember, we have to stay in quadrant 1. So we are going to need this area. Okay, there's our feasible region. Let's find the corner points. Where are corner points? Here's one of them. Here's one. Here's one. And here's one. Make sure we can find it right here. Here. Okay. So let's find those corner points. This one ought to be easy to find. You can just write that one down. This one we can just write down. This one we can just write down. So there's really only one that we need to do work to find, and that's right here. Okay, and for that one we need 6x plus 2y equals 36. We also need 2x plus 4y equals 32. Let's multiply that top equation by -2. That'll give me -12x. -4y equals -72. If we add these, we have -10x equals -40. And so my x is 4. Put that into one of your equations. So 6 times 4 plus 2y equals 36. So 2y is equal to 12, and therefore y is equal to 6. So we have the point 4, 6. So we make a table that has our corner points and our objective function. what was our objective function? Z equals 10x plus 20y. Okay, since we have an unbounded region, we want to think about what is happening as x and y go out to the unbounded area of our feasible region. Here, y cannot get infinitely big. It's bounded by this horizontal line, y equals 20, but x can get very, very large. So if we whatever we have for y, let's say 20, if we keep getting x bigger and bigger, what's going to happen to z? It's going to get huge, right? So this thing would not have a maximum. So I check and make sure. If I were being asked to find the maximum, I would say that no maximum exists, but I only need the minimum. And so I know I am going to have one of those, and it's going to occur at a corner point. So my corner points are 0, 18, 0, 20, 16, 0, and 4, 6. So when I calculate these, here I get 20 times 18, which is 360. 20 times 20, because remember my x is 0, this gives me 400. Here I will get 10 times 16, which is 160. Here I get 10 times 4 plus 20 times 6, so that's 40 plus 120, which is 160. So notice something here. We have a tie. Okay. Here we have a tie. These are the smallest numbers, and it occurs in two different places. So what I do is I find those points on here. Here's one of them, 16, 0, and the other one's at 4, 6. That means everywhere along here my z will be 160. So my z will be at a minimum anywhere on the line segment that joins those 2 points. Okay, so that one that I've colored there in blue. So we need to figure out how to describe that. So what we want to do is we want to take that line, so 2x plus 4y equals 32. Let's solve this thing for y. So 4y is equal to negative 2x plus 32. Divide everything by 4, and we'll get negative 1/2 x plus 8 in slope-intercept form. And so here's what we say. We say the minimum is 160. Now, part of writing the solution to a linear programming problem is not only finding the minimum or the maximum, but also saying clearly where it occurs. Here's how we say it. It's going to occur when y is equal to negative 1/2 x plus 8, but it's not anywhere on that line because it stops here. In other words, if I go further to the left or further to the right, we can't have that. So we want to just put some boundaries. We can just put the boundaries on the x. So my x is in between 4 and 16. This way we have clearly described the solution, where the minimum occurs and what the minimum is. So that is one thing that you have to watch out for that can happen with these. If you've got a tie, your minimum or your max will be along that line segment that joins them. What this basically means is that your constant z lines as we saw when we drew the picture earlier, those happen to have the same slope as this line segment, and so therefore instead of hitting a corner, it hits the whole entire edge of the feasible region simultaneously, and that can happen. I hope this helped you understand solving linear programming problems with the graphical method. We will move on to some applications which hopefully will help you even more. Good luck!